Hi everyone, Selamat Hari Raya. So today we want to continue from the previous lecture 4, this is lecture 5, Principles of Parallel Algorithm Design Part 2, where we want to look at another two decomposition techniques that we have stopped in previous lecture. Okay, so let's look at what are the other subtopic that we will learn in this lecture. Okay, so there are another two decomposition technique which are exploratory, and another one is what we call that, speculative decomposition. So let's start with the exploratory first. So what is meant by exploratory decomposition? So in many cases, the decomposition of the problems goes in hand with its execution. Means it's depend on the programmer itself on how they want to decompose the task into several subtasks. Okay, and then these problems typically involve in the exploration search of a state space of solution. Means it's usually involved, okay, in the problems of exploration or searching problems, okay, such as 0-1 integer programming, QAP, or theorem proving, and game playing. So we need to use exploratory decomposition. Means we need to try and error or to search on how to solve the problems, or in this case on how to decompose the problem into several sub problems or subtasks. Okay, so that's why it is called as exploratory decomposition. So this is an example. So let's look at the solution to a 15 puzzle, a tile puzzle. So all of us already know that when we play a puzzle, we need to try and error. So we need to look at which task or which way or which solution that is better than another way or another solution. Okay, so in this example, it shows that a sequence of three moves, okay, three moves, 1, 2, 3, that transform a given initial state. This is the initial state of of the puzzle, to the desired final state, which is this one and D. So we want to get this desired state from state A. So we need to have to try and error lah. In this case, we have three move. Okay, the first one, okay, so at the right side of 6, there is an empty space here. So the first move, it was the 7 moving to the up, and then the second one, 11, will move to the left, and then in C, number 12 will move to the up, and then this is the desired final state that we want to search. Okay, so of course the problems of computing the solution in general is much more difficult than in this simple example. So this is just a simple example, whereby in real, so we need to consider more complicated solution to be solved. Okay, so this is one of the exploratory decomposition problem, right? Okay, so next one. So this is another example. Instead of solve the problems in serial, one by one, step by step, so we can create it or decompose it into several subtasks. Okay, so the state space can be explored by generating various successor state of the current state and to view them as independent tasks. So we have this one, the current state, okay, the state that we want to solve. So we divided it into 4 subtasks: task 1, task 2, task 3, and task 4. So from these 4 tasks, we run it in parallel or as independent tasks. So all 4 tasks execute independently to solve the problem. So if you see here, task 1, okay, it move the numbers, okay, to to the below, to below of the 15. Okay, same goes to the 2, 3 and 4 have different move. So this one can be run independently or concurrently. So as they run concurrently, so task number 4 have solved the problem at the first state. Instead of task 1, 2 and 3, maybe they solve the problem in state 1 or 2 or 3 or 4. So we know that in task 4, okay, the problem has been solved in state number 1. Okay. So next one. So this one, another solution or another problems. So in many instances of exploratory decomposition, the decomposition technique may change amount of the work. Yes. So when we divide the task into several subtasks, so it may change the amount of work, or maybe the work or the task cannot have the balance workload. Okay, and then this change result in super or sublinear speed up. So it might affect the speed up or the performance of the process. Okay, so please consider the diagrams here. So as you can see at the left one, we have one parallel task, which is for triangle here, and then inside the triangle we have M. So M process. Okay. And then same goes to the second one, which is we also have the M process. But the difference is, please look at the circle dot. Okay. So at the first diagram, the circle dot is at the triangle number 3 and located at the left side of the triangle. And the second one, the second diagram, the circle dot is located at the first triangle and is at the right side. So what is the difference is at the total serial work and also the total parallel work. So let's look at one by one. So the first diagram here, so to calculate how many M or how many work that has been done or complete on each of the tasks, so we need to analyze the diagram. So as you can see here, from left to right, it is called as serial work. So we need to calculate lah how many serial work from left to right. 1, 2, 3 and 4. So if we read in vertical way here, it is called as parallel task or parallel work. So in this case, only one level of parallel. So in one level 1 parallel, so we can run or execute 4 triangles at once. Okay. So how to calculate? So we need to consider the circle. Look at the circle. So the circle is located at the third triangle. So we know that the first and second triangle have been completed. So that's why it is stated as 1M and 2M. So how we want to know whether it is 1M or 2M or 1 or M? So you need to look at the third triangle. Circle is at the left side, and then left side, if the circle is at the left side, it is assigned as number 1. So if the circle go through the M until it reach the right side, so then we can assume it as M process. So then the M process is completed lah. So if the circle is at the left side, it's not complete yet. So the process, the whole process is completed when the circle reach at the right side. Then we can call as M. So why it is 1 and 2? Because it is triangle number 1 and this one is triangle number 2. So this one is triangle number 3 and triangle number 4. So that's why the total serial work for this diagram is 2m, 1, 2 and 1. Why it is 1? Because the circle is located at the left side. So how many total parallel work in this diagram? So it is equals to 1. Okay, do you understand on this one, this problem? Okay, Alhamdulillah. So, okay, let's look at the B. So, B, look at the circle. Circle is located at the right side. So, it already go through the left to the right, go through all the M process. So, it not reach the second, third and fourth M yet. So, that's why the total period for this diagram is equals to M. Why M, guys? Because of what? Because it already reached the right side. It has go through the M process. That's why it is equals to M. It only go through for triangle number 1. So it is M. So how many total parallel work? Okay, so in this case, why it is 4M compared to the A, it is 1. Why? Madam nak tanya why it is 4M. Any answer? Why the A or the left diagram is equals to 1 and why B is equals to 4M. We know that these two diagram has one level of parallel process. Kenapa? Any answer? Why? No one to answer? I give you 1 minute to think. Why A is 1, B is 4M? You may write down in our message box also if you don't want to explain verbally. To consider the total parallel work, so you need to look at the circle where it is located, either the left or the right. Any answer? Izati, can you answer? Najwa? Tak ada idea. Seorang pun tak ada idea. Amir? Safia? Semua madam terpanggil dah. Any answer? Any idea? You all jawab je. Teka je. Madam suka je kalau ada orang nak teka-teka ni. Betul. Sebab apa? Kita run in parallel, right? Dia jalan sekali empat-empat tu. And then kalau you tengok is located, the circle is located at the right side, right? So one bila dekat left, actually yang the second, third and fourth M ni dia run sekali. So that's why total parallel work dia dah 4M. So how about A? The idea is like that. So how about A? Kenapa dia 1? Dia tak complete. Betul. Ada tambahan? Kalau you jawab tu, you kena macam explain furthermore tau. Okay, kenapa dia tak complete? Sebab dia still one, dia at the left side, right? So left side means when dia run all the M's, 4M's ni, semua 4M's dalam state 1 lagi. That's why the total parallel work dia 1, bukan 4M. Why 4M? Sebab apa? Dah run all the M. Run all 4M, then it get the complete state. So that's why it is 4M. Kenapa dia 1 yang ni? Dia baru nak run 1, dah stop. Kan? So that's why total parallel work dia equals to 1. Tak complete. No M has been completed. Okay. So that's why dia 1. Dia dapat Okay. So next one. Good try everyone. Okay, so the next one is called as speculative decomposition. Tadi exploratory. Kita explore. Okay, kita cari try and error to complete the process or the work. So in speculative ni kita make speculate. Kita teka. Okay, kita agak-agak. So in some application, dependencies between tasks are not known a priori. Sometimes we do not know the dependencies between the tasks. Kan? Kita agak-agak je bila dah run, when we already execute the process, then we know, oh, there is a dependencies. That task is independent. That task is depend to another task, something like that. So we need to speculate. So for such application, it is impossible to identify the independent tasks. Okay. So there are generally two approach. So in this case, to identify the dependencies, so there are two approach to deal with. So one is conservative approach and another one is optimistic approach. So what is mean by conservative ni, cara lama ni, which identify independent tasks only when they are guaranteed to not have dependency. Cara lama lah. Dia identify independent tasks only when they are guaranteed tak ada. When we confirm there is no dependencies, then we identify the independent tasks. So however, optimistic ni bersangka baik. So optimistic approaches which schedule tasks even when they may potentially be erroneous, means dia confident je, dia buat je parallel or decomposition, dia buat je even though dia kata maybe there is an error. So conservative approaches may yield little concurrency. So because of dia tak nak ambil risiko, conservative ni may get the concurrency task. However, optimistic ni disebabkan dia bersangka baik, dia kata redah je lah. Okay, optimistic approaches, sometimes some of the processes may require rollback, kena undo balik, kena buat semula in order if there is a case of an error. So that one is speculative. Speculative, there are two approaches, conservative and optimistic. Okay, alright. So let's look at the example. So in this case, dia bagi discrete event simulation. Event apa panggil action event. Okay, so macam what are the activities might happen in a problem. Okay, so the central data structure in a discrete event simulation is a time ordered event list. So we need to use time schedule in the event that we have set or we want to decompose. Okay, events are extracted precisely in time order. So process and if required, resulting events are inserted back into the event list. Kalau silap, okay, kalau ada error, we need to include back the event into the event list. So okay, please consider this one. Okay, kita punya activity, let's say we have this kind of activities or event. You get up, you get ready, you drive to work, eat lunch, work some more. Okay, these are the event or activities in our day. Okay, so these activities ni guys, dia buat timestamp. Dia ada time ordered event list. So each of these events may be processed independently. Yes. Some of these event, let's say what else okay. Maybe kita get up and get ready is an independent event. So maybe you eat dinner and drive, you can make the activities at once. Okay, so it shows that it is an independent kan. So that's why dia kata each of these event may be processed independently. So however, in driving to work, you might meet with an unfortunate accident. Sometimes when we already set or define what are the event that we want to process, so sometimes it might be an error occurred in the event kan. So when the error occurred, so we need to restart back. Okay, you might meet with unfortunate accident. That's why dia kata tadi ada accident. So kita tak boleh nak proceed to the next event. Okay, not get to work at all. So we need to roll back. So therefore, we need to implement this one, optimistic scheduling of other events. We have to be roll back. Kita kena roll back lah. Buat balik ataupun reschedule or reorder the event that we have set or decompose. Okay. So next one, another example, instead of event, kita ada satu lagi example, simulation of a network of node. So this is a network, okay. And then an assembly line or a computer network through which packet pass. So you assume this one is the input and then it want to pass the packet, okay, through the network. So the task is to simulate the behavior of this network for various input and node delay parameter. So from this packet ni, we don't know which one has a node delay parameter. Kan? So we need to speculate. We need to assume which one might have the delay and so on kan. So note that networks may become unstable because of what? Kita tak tahu, maybe ada unstable, lagging ke and so on kan. Ada queue sizes and so on. So we need to speculate. We need to use speculate when we want to decompose this task, this problem into sub-tasks. Okay. Alright. Okay, so another one, decomposition is called as hybrid. Tadi dah ada dua kan, speculative and also exploratory. The last one, you might hybrid those decomposition techniques into one. So it is called as hybrid decomposition. Tak semestinya kita boleh guna exploratory saja. Why not we want to combine recursive with data decomposition, exploratory with recursive, so you can hybrid it. So let's say we have this kind of problem. Dia kata in quick sort, they combine recursive decomposition alone limit concurrency. Yes, sometimes when we want to do quick sort, the recursive decomposition might limit the concurrency, might slow the performance of the process. So why not we combine the recursive decomposition with another technique. So in this case, discrete event simulation, dia kata there might be concurrency in task processing. A mix of speculative decomposition and data decomposition may work well. So dia kata instead of using speculative saja, maybe we can combine it with data decomposition that might increase the performance of the parallel processing. So it said that even a simpler problems like finding a minimum of a list of numbers, kan, we might mix the decomposition technique between data and also recursive. So in this diagram, it combine two techniques between data and also recursive. At the first level tu, dia buat data decomposition dulu, dia pecah dua maybe. So that it find the minimum value. Okay, recursive ni apa? It keep on repeat at the next level until it reach the result or solution. Okay, right. Okay, so finish on the techniques to decompose the problem. So now we move on to the characteristics of the task. Okay. So characteristics of the task ni ada 3. Why we need to identify or consider the characteristics of the task? Because of once a problem has been decomposed into independent tasks, sometimes it might give an impact to the performance. Guys, because of the choice, we don't know which technique is better than other techniques, right? So we might consider the characteristics of the task before we choose the correct algorithm. Because of what? We want to make sure the performance is better than the serial process. Okay, so there are 3 characteristics. The first is task generation. Second is task sizes. And third one is size of data associated with task. So we need to consider these 3 characteristics. So let's look at one by one. Okay, the first one is task generation. There are 2 types of task generation. How we want to generate the task, either static or dynamic. So what is meant by static, which is the concurrent task can be identified a priori. We can identify earlier before we do the concurrent or parallel process. So what are the example? Matrix operation, graph algorithm, image processing, and other regularly structured problem. Structured problem, we know what happened from A to Z, from the beginning and from the until the last process. Okay, until we get the result, we know exactly what the process that we need to execute kan. Okay, so that's why you can implement static task generation. So this can typically be decomposed using what? If you know exactly the concurrent task, okay, so you can implement data or recursive decomposition technique. Okay, okay. If you do not know the concurrent task, okay, earlier, when we execute the task, then we know, oh, this one we need to try and error kan. So that one we call as dynamic task generation. So if you overcome to this problem, so you might use either exploratory or speculative. Contohnya apa? Puzzle board, yang main game kan, chess ke and so on. So you can implement this kind of decomposition technique. So task generation, before you create or you want to choose the technique, so you need to consider whether the concurrent task can be defined at earlier stage or not. If yes, it is static task generation and you need to use data or recursive. If you do not know, it is called as dynamic task generation and you might use exploratory or speculative. Okay, that one is related to task generation. So let's look at the next characteristics, which is called as task size. So we need to consider the size of the task before we want to decompose the task. So there are 2 types of sizes, uniform or non-uniform. If uniform, it is said as the size are all the same. Kalau non-uniform, the opposite of the same size lah. Okay, non-uniform task sizes may be such that they can be determined or estimated in earlier stage or not. Okay, for example, okay, in the include discrete optimization. So when we deals with optimization problems, we sometimes cannot identify or cannot do not know the size of the task that we want to decompose. Okay, so it is difficult to estimate the effective size when we want to do the concurrent process, right? So basically, when we want to decompose, you need to consider the task size. If you know the task size and then you are sure and confirm that these tasks can be divided into the same size, so you can do the decomposition, or else you just use a serial process. Okay, because it might degrade or downgrade your parallel performance. Okay. So the third one is called as size of data associated with tasks. The second one is about the size of the task, but this one is size of the data itself that related with the task. So the size of the data associated with a task either may be small or large when viewed in the context of the size of the task. Okay, when the task is larger, sometimes the data also large. So vice versa, when the task is smaller, of course the data that associate with the task is also small. So a small context of a task implies that an algorithm can easily communicate. Yes, of course, when we use or we decompose a smaller task or small data, it's quite easy, okay, or it's easier for the algorithm to process, okay, or to make a communication between the tasks, okay. And then if we use a large size of data in the task that we have decomposed, maybe quite difficult to make the communication between the tasks because it need more time to communicate. Okay, and then an algorithm may attempt to reconstruct. Sometimes we need to reconstruct back the context or the algorithm to consider the large size of data during the parallel algorithm being executed. Okay, so in this case, it said that 0-1 integer programming is quite difficult or needs large context ties or communication between the tasks, right? Okay. Okay, so characteristics of the task interaction. There are two types of characteristics of task interaction. So in this case, we want to look at what are the characteristics between the tasks when they are communicate with each other. So either static interaction or dynamic interaction. So if static interaction, the task and their interaction are known a priori, means we already know between the tasks can be interact with each other, and in this case it's simpler to code lah, to write the code into the programs compared to the dynamic interaction, whereby the timing or interacting task cannot be determined a priori. We do not know which task can communicate with what task. Okay, so it's quite difficult to make the code or to write the code. Okay, and then, okay, for example, in this case lah, using message passing API. Okay, alright. So there are another characteristics which is called as regular interaction and irregular interaction. So regular interaction is a definite pattern. So in this case, the graph sends to the interaction. Okay, definite. We know the pattern, okay, of the task. So we can create the interaction easily. This pattern can be exploited for efficient implemented. However, for irregular interaction, the interaction lack well-defined topologies. We do not know what kind of topologies or pattern, or maybe the pattern is quite complicated. So it is lies under irregular interaction. Okay, the interaction cannot be state or be standardized. Okay, so that one is irregular interaction. So we need to consider this when we want to choose the best parallel decomposition, okay, in order for us to increase the performance of the uh, concurrent processing or parallel processing. Okay, so let's look at the example of characteristics of task interaction. So consider we have 2D mesh ni, dia the interaction is static, regular static interaction in image dithering. Okay, so assume that this is the image dithering process. Okay, and then the process is decomposed into sub processes. Okay, there are 9 processes, and then these tasks actually need to communicate with each other. So how to consider? Okay, basically they have the same size, and then they know in the beginning, in earlier stage, what tasks need to communicate to what task. So that's why they use 2D mesh, okay, to make the communication or to make the interaction between the tasks. So this is an example of regular static interaction pattern. Why regular static? Because we know in earlier stage what kind of tasks need to be communicated with another subtask. Okay, so far so good ke anak-anak? Okay, Alhamdulillah. So let's look at another example. Okay, yang tadi regular, static regular interaction. This one is static irregular. Why irregular? So this is the example of multiplication of a sparse matrix with a vector. Kenapa dia kata irregular? Because of the pattern itself. Okay. So the pattern itself, when they want to interact with each other tu, not all node have the same interaction. Okay. Maybe 0 will interact with 8, 4 and 1 only. So that's why it is called as static irregular interaction pattern. Tak sama Okay. Alright. So next one. Interaction may be read only or read write. So when we talk about interaction, what kind of interaction happen between the tasks? So either read only or read write. Okay. So in read only interaction, task just read the data. Macam biasalah kan, just read the data. So how about read write? So maybe dia boleh read and also dia write or modify lah. In this case, modify what? The data items inside the task or with other tasks. So in general, read-write interaction are harder to code since they require additional synchronization primitive. Yes, you need to imagine when you read the data only, okay, from task 1 to task 2 or task another task, so you just read, you do not write or modify the data to in that task. So it quite simpler to write the code. So however, if you want to read and also write the data inside the task or other task, so it's required much or more lines of code. Okay, we need to consider the interact. We need to make sure whether the data is dependent to another task or not. Okay, it's quite difficult to be coded. Okay, that's why it said it's harder to code compared to read only. So if you imagine if we deals with database, when we want to read the data, we just use select star and so on so on. So when we want to write the data, not only we need to select star, but we need to use another code update or delete or something because we want to modify the data itself. Okay, so that one is the characteristics of task interaction. Okay, so another explanation on characteristics of task interaction. So the interaction of read and write just now, okay, it may be one way or two way. So what is mean by one way or two way? One way interaction can be initiated and accomplished by one of the two interacting tasks because it is one way. So it is one of the two interacting tasks. So if two-way, so both tasks, read write just now, involve in an interaction. Okay, so if you read, just required one action lah, read only, not read and write. Okay, so one-way interaction are somewhat harder. However, one-way are somewhat harder to code in message passing API. Okay, compared to two-way. Okay, right. Habis dah. Okay, any question anak-anak? Oh, okay, yang ni Menda tak nak ajar dulu because this is another subtopic which is mapping technique. Okay, so today we just focusing on another two decomposition technique and also the characteristics of task just now. Okay, ada soalan? Okay, just now. Okay, so I want to conclude on what we have learned for today's lecture. So in the earlier slide, so we already covered the exploratory decomposition. Okay, so exploratory decomposition, you need to know what kind of problem that can be used if you want to implement exploratory decomposition. So in this case, like game, playing, proving theorem and so on, you might use the exploration decomposition. Okay, another one, we also learn on speculative decomposition. Speculative decomposition means we need to assume, we need to speculate. So there are two types of approaches, either conservative or optimistic. Okay, so conservative is what? You already identify independent tasks only when they are guaranteed to not have the dependency. We already know whether the task has dependencies or not. And another one is optimistic. You just assume, okay, there is no dependencies. We just proceed the process. And then if error happen, then we just roll back the process. Okay, that one is speculative. Okay, then another one, we also learn about hybrid decomposition. If all four techniques, okay, cannot increase the performance of the parallel processing, why not we use hybrid technique where you can mix between these four decomposition techniques into one. So we already discussed that this kind of example we can mix between data and also recursive in finding a minimal list of numbers. Okay, for the sake of what? To increase the speed and then to fast the to speed up, increase or the speed up and also increase the performance. Okay, and then to use low memory space. Okay, and then the last one, we already learned about characteristics of tasks. Okay, so before we want to consider the decomposition technique that we want to use, so we need to consider the characteristics of the task. So there are three characteristics just now: task generation, the task sizes, and also the size of the data associated with the task. Okay, so apa lagi that related with task generation? Okay, we need to know lah whether the concurrent task can be identified or not. So we can choose data or recursive or exploratory or speculative. So we need to know the task generation either is static or dynamic. Okay. So what else? We need also to know the sizes of the task. Then we can choose which technique that we can use. So the task size are the two types, either uniform or non-uniform. Okay, so if uniform, we know in earlier stage, so we can divide the task into small size, small same size or the same size. If there is non-uniform task sizes, it's quite difficult for us to divide it into same size. Okay, all right. What else that we learn? Okay, size of the data itself that associated with the task, not only the size of the task, but the data that we use inside the task also need to know the size, either small or large. So because of what, if this with small data, we need to write the algorithm itself, the parallel algorithm. Okay, so it might affect okay, the performance of the parallel processing. Okay, lagi what else that we have learned? Okay, the static interaction, okay, between the task, either static or dynamic. Okay, so interaction ni actually deals with read and write. Just now, if you still remember, either it read or write. Okay, then we know the regular, irregular interaction pattern. If regular, we might use this kind of structure, okay, to demesh of, or if irregular, you might use this kind of pattern, okay. Okay, then this one, read only and read write. Okay, that one is related to task interaction. Okay, all right. So that's all. If there is no question, please answer my question in our Google Classroom. Okay? Ada soalan? Ada apa-apa nak tanya? Pasal kelas ke? Tak ada eh? You all mengantuk makan kuih raya ke? Okay. So kalau tak ada, Madam nak end discuss. Thank you so much for participating for today's lecture. Okay, so that's so we meet on Thursday morning. Okay, thank you so much.